Hi, I am Krishnarjan and welcome to Max Plan. Today we shall try to understand the origin of the exponential function. We have all seen the exponential function at one point or other in our lives. The constant e, which is closely associated to the exponential function, appears in all walks of science and technology. In fact, many fundamental physical processes that we see all around us follow exponential growth or exponential decay. From the cooling of a hot cup of coffee to the decay of a radioactive nucleus, exponential growth and exponential decay is everywhere. But what exactly does this mean? To put it in simple terms, the increase or decrease of some quantity depends on how much of that quantity is there to begin with. We shall make this a bit more precise later on in the video. Historically, it was Jacob Bernoulli who first came across the number e while he was calculating interests. He came up with the expression limit n going to infinity 1 plus 1 by n to the power n. It was Euler, 50 years or so later, who came along, called this number e and proved some really cool properties about this number. For example, he showed that e has the following expansion. E is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, etc. Rightfully so, this constant is called the Euler's constant. But in this video, we are interested in something called the exponential function rather than the number e. The exponential function is defined as the following series. exp of x is equal to 1 plus x by 1 factorial plus x squared by 2 factorial plus x cubed by 3 factorial, so on. If we plug in the value 0 for x, we can see that the exponential of 0 is 1. Similarly, the exponential at the point 1 is equal to the constant c that we saw earlier. Now, at first glance, the definition of the exponential function might seem very complicated and scary even for the untrained eye. But this is a very natural definition and in some sense the only answer to a very natural question. We shall try to understand why this is so in this video. More precisely, we shall observe some natural phenomena, and in trying to understand those phenomena, we shall see how the exponential function comes up very naturally. First, suppose we plot the changes in temperature of a hot coffee mug kept at room temperature. Say the initial temperature is 60 degrees Celsius and the room temperature is 30 degrees Celsius. When the temperature difference is large, the coffee cools much faster, and as the difference in temperature delta T becomes smaller and smaller, the speed at which the cooling occurs also slows down. Or, in other words, the rate of change of delta T is proportional to delta T. This is known as Newton's law of cooling. Something very similar happens in the decay of a radioactive nucleus. In all the above examples, we saw that the rate of change of a function is proportional to the value of the function at that point. In terms of calculus, this translates to saying that d by dx of f is proportional to f. So, we need to construct a function which is proportional to its own derivative. Let us make things simpler and assume that the derivative of a function is itself. Or, we are making the assumption that d by dx of f is equal to f. If you don't know what a derivative is, just think of differentiation as a box which takes in a function f and spits out another function which we call as f prime. Let us look at some examples of functions and their derivatives. If you take the constant function f of x is equal to c, then the derivative is 0. If you consider your f to be the identity function, meaning f of x is equal to x, then the derivative is 1. Similarly, if you take your function f of x to be x squared, then the derivative is equal to 2x. More generally, if you take your function f to be of the form f of x is equal to x to the power n, then the derivative of f is equal to n into x to the power n minus 1. Furthermore, differentiation satisfies a property called linearity. This means that if we have two functions f and g, the derivative of f plus g equals the derivative of f plus the derivative of g. Similarly, the derivative of the function c times f of x, where c is some constant, equals c times f prime. Now, we can easily differentiate polynomials. For example, consider the polynomial x squared plus 3x plus 1. If you want to differentiate this polynomial, first you take the derivative of x squared, which is equal to 2x, and then you add the derivative of 3x, which is equal to 3, and the derivative of 1, which is equal to 0. Along with the derivative, there is a very important concept of the antiderivative. The antiderivative of a function f is any function which we denote by f to the power bracket 1, such that the derivative of f to the power bracket 1 is f. In some sense, the antiderivative, as the name suggests, is the opposite of the derivative. But there is a very important caveat. Let us take a simple example to demonstrate. Let us try to find out what is the antiderivative of the function 2x. Now, from the table that we had above, we can see that x squared is one function whose derivative is 2x. But the next question that arises is that the only function? Clearly, if we consider x squared plus 1, its derivative is also 2x. In fact, we can take x squared plus c for any constant c. This gives us a family of antiderivatives of the function 2x. Now we ask the question, are there any more? The answer to this question is no. This is known as the fundamental lemma of calculus. The fundamental lemma of calculus says that given a nice enough function f, the antiderivative of f is unique up to addition by constants. In layman terms, this means that if we have two antiderivatives f to the bracket 1 and g to the bracket 1, then their difference is a constant. Let us come back to our original question. We are trying to figure out a function which is its own derivative. Suppose we call that function as e of x. Let us ask the question, what is the antiderivative of e of x? Since the derivative of e of x is itself, any antiderivative of e will be of the form e of x minus c1, where c1 is some constant. Now you can consider asking the question, what is the antiderivative of e of x minus e1 of x? And if you do that, you will get e1 of x minus e2 of x is equal to c1 of x plus c2 for some constant c2. Here we have denoted e to the power bracket 2 as the antiderivative of e to the power bracket 1. And if we keep repeating this, we will get e2 of x minus e3 of x is equal to c1 x squared by 2 plus c2 x plus c3. Now, if we keep doing this, and if we consider the sum of all these terms, on the left hand side you will have e of x, because your e1s and e2s and e3s all get cancelled out. To find the sum on the right hand side, let us denote c1 plus c2 plus c3 etc. as c. So you can see that on the right hand side you will have a series c plus c times x plus c times x square and so on. If you take the constant c outside, you will get your answer as c times 1 plus x by 1 factorial plus x squared by 2 factorial etc. As you can see, we started from some natural observations all around us and we naturally arrived at the exponential function. I hope you learned something new today, And as always, thank you for watching.